In this section, we continue our discussion of the applications of exponential functions and logarithmic functions. Newton's law of cooling. As you recall, before when we talked about the growth model, exponential growth decay model, I said that if y represents the quantity or amount of something being modeled, then the rate of change of that something, the rate at which that material, that substance increases or decreases, which is denoted by y prime, the rate of change of increase or decrease, is proportional to the amount y itself. And that gave us the exponential growth decay model. It is a growth model if k is positive. It's a decay model if k is negative. In Newton's law of cooling, the rate of change of temperature, the rate of cooling, is proportional not to the temperature, but to the difference between the temperature and the surrounding temperature, the temperature of the surrounding environment, or usually it's called the ambient temperature. So, Newton's law of cooling says that the rate at which a body cools is proportional to the difference in temperature between the body itself, so this is the temperature of the body, and the environment, the temperature of the environment around it. It's like you put a cup of coffee in a room. The temperature being studied is the temperature of the cup of coffee, and the temperature of the room is the environment temperature, the ambient temperature. So instead of T for the temperature of the body, here we use f of t. It's the same thing. Okay, so this is the temperature of the body that is cooling. If you solve this equation, just like we solved this to get this, if you solve this equation, you get this model, Newton's law of cooling. The temperature f of t of the body at time t in appropriate units after being introduced into an environment having a constant temperature of T0. So T0 is the ambient temperature, the temperature of the environment. Okay. Example. A pot of coffee with temperature 100 degrees centigrade is set down in a room with temperature 20 degrees centigrade. The coffee cools to 60 degrees centigrade after 1 hour. Now, to determine C, okay, at 0, initially, at 0, the temperature, a pot of coffee with temperature 100 degrees centigrade. Okay, so this is the initial temperature. Is equal, okay, so this is the initial temperature, is equal to T0, the temperature of the room, the ambient temperature, 20 degrees, plus C e to the minus k times 0. Okay, so this is initially when the time is 0, the starting time. All right, e to the power 0 is 1, So what we have is 100 minus 20 equals C. So C is 80. So C is the difference between the initial temperature of the object and the temperature of the room. Okay, the model becomes f of t equals T0, which is the temperature of the room, plus C, which is 80, e to the minus kt. Now we're told that after 1 hour, so when t is equal 1 hour, after 1 hour, the coffee temperature becomes 60. Okay, so 60, this is f of 1 hour. 60 equals 20 plus 80 e to the minus k times 1 after 1 hour. T is 1, which means 80 e to the minus k equals 60 minus 20, which is 40. Now we need to solve for k over here. Solving for k will give us the final statement of the model. We need to apply the ln. Okay, first e to the minus k equals 40 over 80, which is 1 over 2. Ln e to the minus k. Ln and e cancel out, so minus k is ln 1 over 2. Now, ln 1 over 2 is ln 1 minus ln 2.
That's what I figured.
So minus k equals ln 1 minus ln 2. Ln 1 is 0. So k is ln 2. Ln 2 is using the calculator 0.69314. So I'm gonna keep only 4 decimal places. So finally, our model becomes, after figuring out what is k for this specific problem. Remember what I said before when we discussed, we don't need to use the units here, when we discussed exponential growth and decay, I said that k is a constant that is specific to each problem, and it is determined by experiments or observation. So this is our experiment here, which determined k. Okay, so that's our model for this specific problem. All right, find the temperature after half an hour. Temperature at time equals half an hour equals 20, 80, e to the minus 0.6931 times half. T is half. So we need the calculator for that. So this is 20 plus 80 times make sure you practice this using the calculator, otherwise it's gonna take you lots of time to do that. So this is 0.7071 times 80 plus 20. So the temperature after half an hour goes down from 100 to 76.568, so 57. After half an hour, the temperature goes from an initial temperature of 100 to 76.57. How long will it take for the coffee to cool to 50 degrees C? Now we want f of t to be 50 degrees. So we have to find t. Okay. Usually math problems are like that. Applications of math problems. You have an equation that has more than one variable, one unknown. Okay. You're given some of the variables. You have to find the last one. In this case, we are given f of t. We need to find t. In part B, we were given t. Find f of t. All right. F of t, we go back to our equation. F of t is, we're told, is 50. So 50 equals 20 plus 80 e to the minus k times t. Okay, so the unknown in this last problem is t. All right, take 50 to the other side, 20 to the other side. 50 minus 20 is 30 equals 80 e to the minus 0.6931 t. Divide 30 by 80, so 3 over 8 is equal e to the minus. Now we apply ln to both sides. Ln 3 over 8. Ln e cancel out on the left side. On the right side, ln cancels with e. So we're left with the input of the e, 0.6931 t. Okay. T equals minus, because we have a minus here, minus ln 3 over 8 divided by 0.6931. Using the calculator again, 3 over 8 ln divided by 0.6931. So it will take 1.42 hours for the temperature to go from 100 to 50. Almost 1 hour and a half. Okay. In chemistry, the pH of a solution is defined by this equation, where in this equation, okay, this is the pH. It's a measure of the acidity of the solution. In this equation, this is the concentration of the hydronium ion in moles per liter. Okay, how much of this ion is present, the concentration per liter. The pH value is a measure of the acidity or alkalinity of a solution. Pure water has pH of 7. Substances with pH greater than 7 are alkaline, and substances with pH values less than 7 are acidic. It is customary to round pH values to nearest tenth. Okay. Find the pH of a solution with hydronium ion concentration equal to 2.5 times 10 to the power minus 4. Okay. That's simply an application of the formula. Minus log, this is base 10. Okay, if there is no base, it means the base is 10. Minus log of this 2.5 times 10 to the power minus 4. Using the calculator, log base 10, let me see if I have that on my calculator. Yes. Okay, so this is 3.602. Okay, after 0 we have a 2, less than 5, so we keep it as 0. Alright. Find the hydronium ion concentration of a solution with pH 7.1. So as you can see in this equation, there are two unknowns: the pH level and the hydronium ion concentration. You're given one, find the other. Okay, in the first part we were given the hydronium concentration. Find the pH level. And the second one, we're given the pH level, find the hydronium concentration. All right, so part B, we have 7.1 equals minus log to the base 10 of the hydronium ion concentration per liter. Alrighty then. Take the minus to the other side, and this is 10. So 10 to the power 7.1 is equal to what we need. Okay, this minus goes over here. So we have 10 to the minus 7.1 equals log, sorry, we cancel the log. Okay, this equals the hydronium concentration. Then to the power minus 7.1. This is what I have is 0.000 7 zeros. 794. Okay, or this is 7.9 94 times 10 to the power 1, 2, 3, 4, 5, 6, 7, 8. 10 to the power minus 8.